Hello, I'm Iddo Tzameret from Imperial College London, and in this talk I'm going to present our recent work about feasible constructive proof of Schwartz-Zippel Lemma, and this is a joint work with Albert Atserias from UPC Barcelona and CRM. So let's start with the talk. First, I'm starting with polynomial identities. Polynomial identity and polynomial identity testing, whose acronym is PIT. So in this problem, I'm giving a kind of an expression, which is basically algebraic circuit or a formula. So it's a syntactic expression that computes polynomials over a field. So I'm given, let's assume, n variate polynomial, and I want to compute it with an algebraic circuit on a kind of an expression, and the expression has two symbols for plus and times. F denotes usually the field. And the question is whether this expression computes the zero polynomial. And here is an example. So this example here is just an equation between two algebraic expressions. This means times here, implicit times, and this is a big sum, times 3. And then here in the right-hand side, we have a more complicated algebraic expression with variables xi's. And actually, this is Newton identity for k equals 3, and these are indeed two identical polynomials. Namely, they are different formulas, but they compute the same polynomial. And the question of PIT is to decide this, whether indeed the equality as formal polynomial hold. PIT is usually about testing whether a algebraic expression equals computes the zero polynomial. So this is, we just flip the side here, and then we say this equals 0. So equality between two expressions and equals 0 is the same. So let's discuss again polynomial identities. So if I have E in n variables x1 to xn, then I say they compute the zero polynomial. I just want to explain two interpretations here. One is the usual, the formal one, the correct one, so to speak, is I just expand out all and group all equal monomials, and this expression computes the zero polynomial if all coefficients of all monomials are 0. So zero polynomial as a formal polynomial identity means that each coefficient of every monomial in the polynomial is 0. The second interpretation is not the formal one for us, but it is important to think about this, because this is what we can sometimes express in the theories that we shall work with, is that we evaluate it at any point and we always get 0 as the value of the polynomial in that point. So for all points over the field, we're going to get 0. Now, when f is big enough, then two interpretations are equal. It's not entirely trivial to prove this. What is the complexity of PIT? Let's assume over the rationals. So this problem is known to be in co-NP, right? As is written here. It's also known to be in co-RP, right? And co-RP is explained here as the class of problems where no instance, the non-identities in this sense, can be efficiently confirmed using randomness. So we know it is in co-RP. It is unknown whether it is below here in NP or in P, though it is conjectured that PIT is actually doable in P, namely in deterministic polynomial time, but this is a big open problem. Now, another thing that we shall need and use in this work is the fundamental theorem of algebra, FTA. So, just to recap this theorem, it is the following. In some sense, it is Schwartz-Zippel version with one variable. So Schwartz-Zippel Lemma, and I will explain the details later on, subsumed the fundamental theorem of algebra when the number of variables is 1 of the polynomial. So every non-zero degree d univariate polynomial over the complex number has exactly d roots in C. That is the fundamental theorem of algebra. Now, we split it into two directions. One is the greater than or equal FTA, so greater than or equal d roots. So that's by algebraic closure of the complex numbers. But if we consider other fields, and we shall consider other fields, then we have the following: FTA less than or equal. So this direction, less than or equal than d roots, is available in every field and is done by Euclidean division for polynomials, and we shall use this in our work. Now we come to the main theorem or result that we shall discuss in this work is Schwartz-Zippel Lemma. Now this is known for about 100 years from a work of Ore, and later on from Schwartz-Zippel and other people. So this is the statement: for every field F, every finite subset S of F, every number of variables N, and every polynomial P in the ring of polynomials over N variables, we have the following. If P is not the zero polynomial, then this happens. Namely, if I choose randomly from S to the N random points in this cube, or S cube, if I choose random points, then if P is not the zero polynomial, then the probability that over these random points P is zero is somewhat small in this sense. It is at most the individual degree of P, where individual degree is the maximal power of a single variable in the polynomial, times n, the number of variables, over the size of the S we chose, namely the cube. So as S becomes bigger, this probability is smaller. So as we choose from a bigger cube, then we have better probability to not hit a wrong or a bad example where a non-zero polynomial actually is evaluated to zero. And indeed, this means the following. So as a counting statement, it just means that the number of roots in the cube Sn is bounded by this. So individual degree times number of variables times the size of S, the points we choose, to the power of n minus 1. And that is the Schwartz-Zippel lemma. Now there's other versions with a total degree. I will mention this later. But this is one version, and it's sufficient in most cases, I believe, in application in complexity. Right, so sometimes you consider to replace this by the total degree, D. So let's look at this example. So this is just an example of a polynomial with two variables, x1 and x2, and its name is p. And this is a nice or helpful diagram to explain things. So below here is the plane of x1 and x2. This is the x1 axis and this is the x2 axis. Now I'm taking f here, the field, to be the reals, let's assume, and s, the size of which the cube is going to be consist of, is going to be just this discrete 5 points. So 1, 2, 3, 4, 5. Of course, n, as I said, n is the number of variables, it's 2, and d, the degree of the polynomial that I've written here, is of the individual degree is going to be 3. Now let's look at this graph. What it means is at the bottom I put the cube s to the 2. So here it's 0.55 and so forth. So there's 25 points here, and on the axis, this vertical axis, I will put the value of p in this point, in the point of x1 and x2. And I've written it like this, and just for the sake of clarity, I've written this as yellow, this 5 points. It's not necessarily correct for this polynomial, it's just an example where I say, oh, these are the roots. So here the points are 0. The value of the polynomial, right? In this case, if you look at the number of roots here in s to the n, then what you get from Schwartz-Zippel will be this, at most 30. So because we chose s to be too small here, it doesn't really give us meaningful result, because then the cube is 25 and this is 30. So it's not a really good example here, but if we've taken s to be bigger than 5 points, this would be exemplify a good case of usage of Schwartz-Zippel. Now we are going to discuss the first, which is the standard proof of Schwartz-Zippel, and this will be for the total degree version. So we simply go by induction on n, the number of variables in our multivariate polynomial. The base case is just the fundamental theorem of algebra, the less than equal case direction, and this is when n is equal 1, the polynomial is univariate. So this is immediate from this FTA. The induction step is as follows. I have a polynomial with n plus 1 variables, x1 to xn plus 1, and I write it as a univariate polynomial as follows. So I write it as p of x n plus 1. And so this is a univariate polynomial in one variable, xn plus 1, and written as a power sum here, and each power xn plus 1 to the power of I is multiplied by pi, and pi itself is a polynomial in n variables, x1 to xn. And the degree we know, we assume, is denoted by d. So our polynomial, multivariate polynomial, is of degree d. Now let M be the maximum I such that Pi is not identically 0. We know it exists because P itself, the R input polynomial, is non-zero. So we know that when we write, when we have this, our polynomial, there is one of the PIs that is non-zero. So then the degree of PM is at most D minus M, since the degree of the whole polynomial is D. So this is written here. Now, what we do is very simple. We divide it into two cases, the good and the bad cases. So in some sense, it is one part is a reduction to the FTA, to the univariate case. And then we shall consider what happens if this is impossible, and this is the bad case. So for every fixed x, so x is here is from x1 to xn in s to the n, right? So our p, our initial polynomial is in n plus 1 variables, but here we look at the first n variables. So for every fixed point in s to the n, there are two cases. So here it's PM, yeah, not like I wrote before PT. So if PMX is the good cases, it's non-zero in this point, then by FTA, the number of S roots from S, taken from S, each coordinate is taken from S, of the univariate polynomial Pxn plus 1, given this choice, x is at most D. And this is, as I said, by FTA. So this is good. We reduce it to the simple case. What happens if it's bad, if actually PM is 0? So in this case, it might be that actually all the polynomial here is all the values are 0. So what happens is that we might get the number of S roots given this choice of x when we extend it to the n plus 1 coordinate is going to be at most S, right? At most the size of S, so because everything is 0. So we don't really have the small bound of D. So this is not good. But by induction hypothesis, we can actually bound the number of these kind of bad x's. And so by induction hypothesis, the number of these bad x's is at most D minus M times, because this is the degree of PM, times S, size S to the n minus 1. This is from Schwartz-Zippel for n variables. So induction hypothesis. So now we just plug this in, so we get that the number of zeros is at most this D minus M times the size of S to the power of n, and plus M times S to the power of n, and this is equal D times S to the power of n. So this is the Schwartz-Zippel total degree version, and this is proof by induction, standard proof. Now the second proof that I want to discuss is Moshkovitz 2010. So this is in some sense induction free proof. What happens here is we have this polynomial Px1 x2, this the running example for us, and we have these coordinates x1 and x2, and this is the support here, the 25 points that I discussed before, and we want to see we want to bound again the number of zeros. Right. So I wrote here B. So B is a line in this plane, in the x1, x2 plane. So it is defined by a point in s to the 2, right? Or s Cartesian product of s, because this is just for the sake of example. We are in a polynomial with 2 variables, so that's why I put here s times s. So A and B are 2 points, and B will be some direction here, some vector here, B written in green on this plane. Now what we're going to do is we take this B. It doesn't need to be, and it's not in the picture, parallel to this axis. We take it, this B, and we consider, when we take A is some point, some offset, plus B times Z. So this is a line, this is this line, right? In this picture, it's an example of this line where A is something here, and B is the green line, right? And Z is the variable, and Z ranges over S. So when we consider this line, and here in green, the n-variate P, in this case n is equal to, becomes a univariate polynomial. Q, I wrote it as Q in the single indeterminate Z equals P A plus B times Z. So this is the line. And here in the example, if for instance B is 1 and 3, then that's what you get. This is what I mean by P, and here this line. So you do it coordinate wise. So it's quite simple now. Now this is B, and we consider the polynomial when the input, the parameters are over B, over this line. And because and if we make sure that B is such that for any choice of A from S times S, for any offset, B is going to be such that QZ is not equal 0, then what we get is the following. This, our polynomial P restricted to this line, is now, by assumption, non-zero polynomial, and so by FTA, the fundamental theorem of algebra, we know that its degree is at most d, so we know that on this line there is at most d roots. Now we continue with the other lines, given all the other a's that we can have. Of course, we might have the same, we might have 2 a's that gives us the same line, but we consider only the set of different lines, and there will be only 5 of them in this case. And so we'll have, over each of the line, we'll basically cover all the 25 points of S times S. And we have only 5 lines, so we'll have basically S, which here is 5, the size of S5 times D, to cover all the roots, to bound the number of roots. The trick here is to actually find this B. It's not hard to find this B, such that for all a QZ is non-zero, namely over these lines, all of these lines, the polynomial restricted to these lines is non-zero. So that was quite simple idea, and in some sense it's reminiscent of the standard proof, because again it uses, in some sense, it uses FTA, and then considered how to use it on all possible, in this case, all possible lines that cover the space S times S. Now, Now I'm going to explain our new proof, which, as I said, will be constructive. I will discuss what it means precisely to be constructive. But intuitively, it's also easy to see why it is constructive, because the concept that we will build will be polynomial time computable. Now, and here is the proof. So we give a new proof of the following equivalent statement of the Schwartz-Zippel Lemma. In our case, it will be for the individual degree version, but as I mentioned before, for application, they are all equivalent or useful for the sake of applications, as useful as each other. Now, the proof is the following. Right, so we have P yeah, so actually I change it to X are the indeterminate. So let Px be an algebraic circuit with n variables and d individual syntactic degree. So here I said the following: it's going to be an algebraic circuit or a polynomial, but for the sake of the theories, we're going to have this as an algebraic, given as an algebraic circuit, but you can consider it just as a polynomial. So Px is a polynomial with n variables and d individual syntactic degree. Then either Pb is 0 for all b in the field. This is a field, and to the power of n. So it's completely 0 everywhere. Or Pb is equal 0 for at most size of s n minus d to the n minus d times d, the individual degree, times n points in the cube s to the n. So either the polynomial is 0 everywhere, or the number of roots in the cube, and we choose this s, this finite s, over this cube, the number of roots is bounded by this number. So a size of s to the n minus 1, and here we get d times n. So let's see the strategy for the new proof. So given p in nx variables and some point in f to the n, we define the following function. Now this function is going to be explicit. I'll describe the function. It's not that complicated, and it's polynomial time computable and deterministic. So the point is this: you are given b a point in the space f to the n, and you define f parameterized by p, the polynomial, and this point b. Now this function is defined from this set, which will be a set of codes, to s to the n. Now it will have the following properties. It's going to be, as I said, it's going to be codes for all, but it will be codes for all roots in s to the n, given the b we got is good, namely b is a witness that p, the polynomial, is non-zero. And it will have the following properties. It's going to be onto roots, and I write roots s p to denote the set of roots over the Boolean cube s to the n, where the roots are for the polynomial p of the polynomial p, and they are, of course, they live in s to the n. So this function f FPB is going to be, if B is indeed a good point, then it's going to be onto the set of roots, SP. And so then this will be already enough to prove Schwartz-Zippel. Why? Because the size of this, the size of this, of the domain is going to be obviously at most s to the n minus 1 times d times n. N is the number of variables, d is the individual maximal individual degree. And if there is a function which is from this set of codes of this size, which is onto the set of roots, then it must be that the set of roots is at most the size of the domain, which is bounded by this. So this will be enough, but we also show, and this is important for us, that this is FPB is explicit and polytime deterministic, given any such good B, and it is also invertible in polynomial time deterministic, given this B. So we're going to be able to also invert, given a root, we're going to invert it into its code. So how do we define this function precisely? So given a root C in root SP, right? So this is going to be from C1 to Cn, each coordinate is from S, and a non-root B, so it's going to be from F to the N set minus root SP. We have the following. Right, this is just the setup. So PB is non-zero by assumption, because it's not a root, and PC is a root. Now, what can we do? So here you can think for a second. What does it resemble from computer science theory? So this resembles kind of the starting at the setup of a hybrid argument, and this is what we do. So we define this hybrid argument as follows. So we have B, we start with B, and we know it's non-zero, and at the bottom of the hybrid is just precisely argument is precisely this kind of argument. It's a row where you start from one vector, and then gradually add the other vector and find the place where they differ. So we start from B and we end up with C. When we plug in B into P, it's non-zero by assumption, and when we plug in C into P, it's zero by assumption. So there must be, at least the first time, then we switch from non-zero to zero, when we start gradually plugging in C, the coordinates of C, into P, replacing those of B, like this. So here I wrote it in this two rows where the switch appears first. Here it's non-zero, here it's zero. So there must be this first time that this happens, and here it's happens in a coordinate t, for example. So here it's bt, and here when we switch bt to ct, with everything else as the same, is with c, and above this everything is from b, beyond this, then this is equal to 0. Right, so that's the assumption on the hybrid argument, and what is the actual argument is as follows. And by the way, below this, we don't know. It doesn't matter if it's 0 or 1. It might fluctuate between 0 and 1 again, but at the end it's going to be 0. So what is the argument? So first we consider a univariate polynomial q in z. So we replace this coordinate, the tth entry, with z, variable z, and all the others are fixed. It's from c and beyond it from b. So it's a univariate polynomial denoted q. Now, what happens is the following. Now, I put the hybrid here for convenience. So what happens is this: let's start from a root here. So we start from a root C1 to Cn. Assume it is a root. Now, and of course we assume that B is a non-root. So what we can do is we do the hybrid and we find this T here. So to encode this root with the code here, we're going to take T and discard this BT and CT. We don't need it because we're going to encode it with T, but we also need to encode it with I. So we encode it with T, the coordinate, and I, and discard it. So we have only the prefix C1 to CT minus 1, and then BT plus 1 to BN, and note not BT or CT. And we put T and I. Now I didn't tell you what is I. So T is the hybrid, and I is simply the following. So we look at this Q, univariate polynomial, at the bottom, and by assumption, we know that it is a non-zero polynomial, but CT is one of its zeros by assumption. So CT is by definition the ith root of this univariate polynomial QZ for some I. Now we can have an order on S, and we say this is the first one. When we have an order on S, go element by element over S, the set S, and we find out which position the root is. Is it the first root, the second root, the third root, or the ith root, and so forth. So if it is the ith root, we put here I. And that's it. That's the encoding. So it's quite simple. Now, this can be done for any root. And now we show the opposite, that it is decodable. So from this, how to get from the code, how to get the root. So this is obvious. We just reverse this operation. If we have this a1 to an minus 1 and we know t, so we just plug everything here, we know where it's t, and we just need to find this ct that is discarded. But we are also given I, so we know that we just look at this polynomial. We have this polynomial because we have all the elements from AI except Z. So we search for the ith root of this, and then we find it. And this is polynomial time computable. We find it and we know what is CT. And that's it. And we plug it in and we have the full root here. So this is the new argument, and now we're going to see some applications in feasible proofs and bounded arithmetic. So first, just a recap of what is feasible proofs. What do we mean precisely by feasible proofs here? Here we are, as I mentioned, we are working in bounded arithmetic. It's theories which are subtheories of piano arithmetic. Now the question for us will be, what is the weakest subtheory of piano arithmetic, of bounded arithmetic, that can prove this Schwartz-Zippel Lemma and its usual application in theoretical computer science, which is, for instance, PIT in P/poly or PIT in CoRP. Now, what is feasible proof? What is bounded arithmetic? What are the theories we are going to discuss? Of course, I'm just going to recall some notations and say something about them, but you need to look at the paper to understand more about the theories and also reference therein, because there's a lot of literature about these theories. But let's say the intuition is not that complicated. These are just first order formal theories with some set of axioms, the two quantifiers for all and exist, and these are the theories that are usually are of interest. So this is a PV1. PV1, and then subsumed by S12, T12, S22, and so forth until BA, here, bounded arithmetic. Now, for PV1, it's a theory I'll show in the next slide. It's something about this. It's a theory which has induction for polynomial time predicates. And S12 has something like length induction for NP predicates. So this is kind of induction for NP predicates, but it is it's written such that it's on the length of strings. I'll show you in the next slide more or less what it means. Now T12 is induction for NP predicates, not just on the length. And this BA at the top is induction for polynomial hierarchy predicates. Now here we will also work with these following theories extended with an axiom, an important axiom, which is DWPHP, which stands for dual weak pigeonhole principle for PV function. PV is a set of all possible polynomial time functions defined somehow, and this is by some kind of an axiomatic way via Cobham recursion. So PV you just think of as a set of all polynomial time function symbols. And dual weak pigeonhole principle I'll show you in the next slide. And accordingly, S12 can be augmented with dual weak pigeonhole principle for polynomial time functions. And they all sit between S12 and T22. Now, let's see a bit more notation and concepts from bounded arithmetic. So S12 plus dual weak pigeonhole principle over polynomial time functions, PV. So the universe is the natural numbers. It's a first order theory with intended universe, so the elements are supposed to be natural numbers. Now a number x is something between 0 and 2 to the log x plus 1 here, and this encodes, that's by definition of x, so that's obvious inequality for natural numbers, and we say it encodes a string of length size x, which is precisely log x floor plus 1. Right. So if I have a number, it can be of this size, but it can encode strings of this length. And now we have basic axioms for plus times less than or equal size, defined like this, and the smash function. Now the smash function is the following. It's going to allow us to describe polynomial growth for lengths. So, and specifically, it's going to allow us to do x sharp y, which is defined to be 2 to the size of x times size of y. So 2 to the size of x times size of y allows you to have a bound that bounds, upper bounds, numbers whose length is going to be x times y. And so this will allow us to encode polynomial size growth, and the polynomial is going to be of the polynomial in the string size. Now this is I'm just saying this because this explains what is a smash and how numbers actually encodes objects, syntactical objects in the theory, because the theory is just about numbers, but you need to somehow in logic discuss objects which are syntactical, like formulas and so forth, and they are written as binary strings, and so numbers will encode them. And we need to have this smash function in order to be able to encode things, and also to express a polynomial time to polynomial growth in the length of strings. So the axioms for PV polynomial time algorithms. So these are, again, I'm not describing it precisely. It's a set of recursion based on Cobham recursion on notation that defines all possible polynomial time functions. And the length induction for all NP predicates. I do not describe it, but it's a kind of induction for NP predicates. And it's defined like this because this is the notation. Sigma B1 defines NP in this language. Now the dual weak pigeonhole principle, this is important and it's quite simple. What it means is just pigeonhole principle, but dual in the following sense. So if you take a function for PV functions, or for polynomial time functions, so for polynomial time function f, if it is from n to 2n, so the range is bigger than the domain, then there must be a point which is outside the range of f. Right? Because this is a function, so the function, if the domain is n, cannot cover all 2n points. And this is how it is written logically. Exists a y smaller than 2n, such that for all x smaller than big N, fx, the function on x, is not y. So how shall we state and prove the Schwartz-Zippel Lemma in the theory? So the theorem, and this is inside the theory S1-2, is the following. And this was in some sense open. There were some attempts by Dai, Trilla, and Steve Cook in 2010 or 2012 to formalize this. They formalize Schwartz-Zippel, some very special cases of Schwartz-Zippel, but this was basically open for some time. It was interesting because formalization of complexity theoretical results within bounded arithmetic is important and is interesting, and to be able to formalize results in pseudo-randomness or de-randomization theory in bounded arithmetic is important and interesting. And to be able to do this, it is interesting to try to prove Schwartz-Zippel in bounded arithmetic. Now, here is the theorem. P is polynomial of degree D. Actually, it is a polynomial of individual syntactic degree d and n variables given as an algebraic circuit over the integers. So here the degree is individual degree as before, but it's also syntactic individual degree. And this is, you can look up at the paper how this is defined. This is simple, it's syntactic. It is needed to be given like this because you don't know how to compute the precise degree, the actual degree of a polynomial, only the syntactic degree in polynomial time. Then either P is 0 everywhere on Z, that's like what we did before, or for every integer Q and every non-root B, that's the point for this function, encoding function that I described before, which is a non-root, this happens. FPB, it's the same FPB described before, from codes to roots over the Boolean cube S, is the following. Yeah, so actually it should have been here, I change it now, roots in Q and P. So it's the roots of the polynomial P in Q. Q here means the set 1, 2, 3 until Q. So we just take the set of integers 1 to Q. So this will be our S actually, the set S of points that we choose. So for every integer Q and every B that is non-root, we have this function as we described before, and it will be onto. Now this means that in the theory we have this function. Now this is polynomial time, so certainly we have this function, but we can also prove it is onto. And implicitly, this is some subtlety in proof theory and bounded arithmetic, implicitly now, because we just work in S12, this is the number of codes is bounded by this, because that's the domain we'll have. Now it's not in S12 you cannot really estimate sizes of or clearly estimate sizes of sets like this, so that's why it's implicit. It's just going to be this function. When we are going to add existence of this function, and we can prove that it is onto, but it is not clear how to express this inequality in S12. When we next add the dual weak pigeonhole principle, we will be allowed to describe and prove these kind of inequalities. So more formally, I put here the actual statement that we prove. So it's S12, and this is what we encode. The codes, and they are of this size, but it's not really expressible or provable in the theory. And this is onto. And this is what this formula, so you can read this formula, it's quite straightforward. And this means that P is algebraic circuit with n variables and D and a syntactic individual degree D. Now this log means this is a symbol in bounded arithmetic that says that these are more or less small numbers. So they, in the theory, it's a length of some number. It's a log of some number, because, and it is provable in the theory that this is a length of some number, because not all numbers are necessarily provable to be length of something. So that's kind of a technicality in bounded arithmetic, and we prove this statement in S12. Now, application 2 described here is PIT in P/poly. So here we have the following. Let's assume that C is a set of algebraic circuits over Z with n variables, and H is a heading set for C if, and this is the definition, for every non-zero p in C, every non-zero polynomial in C, there exists a point A in this set of points H such that witnesses the fact that indeed P is non-zero. So it hits or catches every polynomial that is non-zero. So H is enough to check. If you want to check for a polynomial in C, it's non-zero, you just need to check the points in H and see if it is non-zero on one of the points, and it must be true. If the polynomial is non-zero and is from C, that H will, there will be a point A such that PA is not zero over it. And if it's small, it's very useful because then you can simply go over these points and in deterministic time, in deterministic polynomial time, check whether polynomial in C given, say, as an algebraic circuit is computes the non-zero, is a non-zero polynomial. Right. Now the theorem is this. So this is already in this theory S12 plus the dual weak pigeonhole principle for polynomial time functions, PV. So the theorem says the following: for every class C of algebraic circuits of a Z definable in the theory, that's some technical definition, or algebraic circuit that we can define in the theory with n variables, polynomial degree and polynomial size. Well, here it should actually be polynomial individual degree, which is also which is also going to be a polynomial total degree, but syntactic polynomial individual degree. And polynomial size, there exists a polynomial size hitting set for C whose points are from Q, remember it's 1 to Q, to the n, with Q is small, is polynomial in the number of variables. So that's our set S that we need to evaluate or use a Schwartz-Zippel over. So it should be bigger than D, for instance, and N. Yeah, so basically this already leads to PIT is in P/poly, because if you have a hitting set, in the theory can say we have a hitting set, and hence we can test, right, for each length, polynomial length, we can just test a given polynomial algebraic circuit, whether it is zero or not. Just checking the points in the hitting set. Yeah, so how do we prove this? I'm just giving you a rough idea. Is the following: we define this function g. So g is going to be a function from C, set of codes of algebraic circuits of some size, some polynomial size. Q to the n, this will be the points A, or it should have been actually B. These are the points B that we used before, that they are the non-roots, potential non-roots, and then the codes, but multiply with R copies. And this will be, the range is going to be roots with R copies. Now, how are we going to define it? That's just the domain and range. The definition is that C here is some encoding of algebraic circuit computing some polynomial P. And then A here is what we've denoted before by B, the non-root, potential non-root. And now we have points in codes which are, if you remember before, the codes were n minus 1 points in S, or here it's going to be Q, and also I and T, two numbers that will encode, T is going to encode the coordinate of the hybrid, and I is the ith root when we consider the univariate polynomial of in Z, where Z replaces the precise T coordinate of the hybrid. So these are the set of codes as before, and given them, we are just going to compute the R coordinate here by our previous F, the coding function. So we have F, P, and A, that's the non-root, and then we take the code and we get the root. So given this code of root, this function can compute the actual root that was encoded by C1 bar. And so for the other ones until R. Now, when R is big enough, what happens is that obviously just by a simple dimension argument, you see that when R is big enough, this is going to be, the domain is going to be bigger than the range is going to be bigger than the domain. Because here we have, if you remember, codes are smaller than the domain of codes is smaller than the range roots. That's the point of Schwartz-Zippel, our version of Schwartz-Zippel. So when you amplify this by taking enough copies R, then you compensate for this. And basically, the range becomes bigger than all this domain. So if the range is bigger than the domain, so what do we know? Well, of course, like the principle of dual weak pigeonhole principle, we know that there's a point outside G, outside the image of G. So if there is a point, it's not hard to show that any vector of R points outside, a point outside this G, is going to be a hitting set, right? Because the set here, G, are taking circuit, and for each circuit which determine our polynomial, just output all its roots. So point outside it will be a hitting set, because it will not be the roots of the set of roots of any polynomial size circuit. So it's simple to see. And because we have the axiom dual weak pigeonhole principle, we know that there exists some point. That's why we needed to have this explicitly. Otherwise, bounded arithmetic cannot necessarily state that even if the domain is smaller than the range of a function, then there is a point outside that is not mapped by the function in the range. So we needed this, and we know that there exists a point outside G, the image of G, and it is easy to show in the theory that this is a hitting set, and that's enough. Now, here I'm going quickly over the hitting set principle. So a collection of algebraic circuit is defined like this, and we sometimes need to assume that M is kind of a description which is smaller than S, in this case, it's going to be polynomially smaller, but this will allow us to have, if the description is small, so C is going to be here collection of algebraic circuit with n number of variables, D syntactic degree or individual syntactic degree, and S is the size, but we need this parameter M, which is description length, and it will also allow us to upper bound the number of possible circuits in each slice, in each n slice. Because the number of this, the 2 to the m is the size of description, so 2 to the m will be the number of possible circuits in this slice. And it will be, if m is, for instance, s to the 1/3, then when we take the power 2 to the m, will be exponentially smaller than 2 to the s. So, fact, for such class of collection of algebraic circuits, there exists hitting set of size of this size. It's not hard to show. And we introduced this definition, hitting set axiom scheme. It's a hitting set for PV function where the PV f is in PV, so and it is a hitting set for f, and this is the precise description written down. So this is the hitting set scheme, which is an axiom scheme, namely it is a different axiom for each different f, and PV and f is a polynomial time function that is the description, take the description of a circuit and builds the circuits. And we say that for these there is a hitting set. When f is a description, it takes the description and of an algebraic circuit and builds the algebraic circuit that compute the polynomial, and we say that for these polynomials there is a hit, for this set of polynomials computed by f, there will be a hitting, there exists a hitting set. And this is the hitting set principle, and we show interestingly that this hitting set principle is equivalent to the dual weak pigeonhole principle in some sense. So specifically in S12, dual weak pigeonhole principle for PV function is equivalent to hitting set principle for PV function. And here are some description ideas from the proof that I do not cover. And this is quite interesting because this relates to the concept of reverse mathematics, the attempt to find minimal axioms that prove certain theorems in mathematics, or show that an equivalence between statement or theorems in the theory and specifically show that if you have some kind of a primitive combinatorial principle like pigeonhole principle, or for our case dual weak pigeonhole principle, and you show that from this principle over some theory, base theory S12, you can prove some statement, some theorem, in this case the existence of hitting set, then it's not just that from this primitive principle you prove the statement, but also from the statement you can prove the principle. So this is kind of a reversal or equivalence principle here, that the primitive axiom is actually equivalent to the statement. Right, and let me summarize quickly. We gave a new proof of Schwartz-Zippel Lemma, and this gives a PAT in P/poly and in co-NP in this theory, and Schwartz-Zippel itself formalizes, so to speak, in S12. You don't need to do a weak pigeon principle if you want to just to express it as the following. If a non-root exists, then roughly many non-root exist, or this is the specific statement that this should have been a V dash proofs. This happens. Thank you very much.